Okay, so we're going to start out with alchemy, history of the atom, and atomic models. Okay, we're going to look at the progression of our idea of what the atom looked like originally, what we thought it looked like, and what we believe it looks like now. Okay, again, it's not something we can see. Okay, they're very, very small, but we have, from their behaviors, we've deduced that this is probably what they look like. All right, so we're going to understand how the theories of the structure of the atom were developed and also how they were changed, okay, and learn the parts of the atom and their characteristics. That's probably a review, okay? What makes up the atom? Three things.
Neutrons, protons, and electrons.
Neutrons, protons, and electrons. Okay, two of those particles are in the nucleus. One of them surrounds the nucleus in what we call the electron cloud. Okay, so you guys already knew that. Okay, what we're going to look at is more, how do I determine or figure out how many protons there are, how many electrons there are, and how many neutrons there are, so I can draw the atom correctly. Okay? In fact, that'll be one of the questions on your unit exam and on one of your quizzes. Okay? I'll say, draw me an atom of beryllium. And I'll expect the particles in correct numbers and correct locations. Okay? Something like that. Pretty easy. Okay. So before chemistry was a legitimate science that used the scientific method and communicated results and had peer review and verification and all of that, there was something that was like chemistry. Okay? It was called alchemy. Alchemists learned a lot about the behavior of matter. The problem is it wasn't a scientific process, and they tended to keep all their discoveries to themselves. Okay? One of the main aims, or two of the main aims of alchemy were to be able to transmute, that is change, common cheap substances into more valuable substances. A very common idea, how can I turn lead into gold? Okay, well, we can't do that, we know that now, okay? But at the time, people's observations of the behavior of matter led them to believe that I can turn this into that. Okay? Because they may have seen, a chemical reaction where they added A and B together and they got C, which was very different from A and B. And so they figured, well, there must be a way for me to change lead into gold. Okay? If I could change these two things into that, why can't I change lead into gold? Well, there's a fundamental difference between a chemical reaction and actually converting one element into another element. Okay? One of those things is possible, the other is not. The other end game of alchemy was to create the elixir of life. Some drink that you could consume that would allow you to be immortal, live forever. Okay? You didn't want to be the person who tried most of those because usually they had the opposite effect. And usually contained things like arsenic and other poisonous substances. Okay? But obviously we've been using chemistry, applying chemistry, for long before we understood how what we were doing worked. Okay? We used, mixed things together and we found that these things would stain cloth, so we could dye cloth with it. Okay? We found that if you added lots of salt to meats, that they would last longer. Bacteria and mold wouldn't grow on them as quickly. So, we would do that. That's using chemical properties to change something or, bring about an end result. You didn't have to understand why it worked, you just knew it worked. Okay? That's kind of the history of human development. Okay? Hey, this works. How? Don't know, but it works. Cool, let's do that. Okay? And then we kind of find out later, oh, okay, this is how it works. Right? Chemistry is very much like that. Okay? If you're looking to write a lot of stuff down, this slide's not super key. Okay? You can write that alchemy, was kind of experimentation without science, or something like that. It's kind of the summary of alchemy. Rain's really coming down. All right, now the idea of the atom was actually developed long before the science of chemistry, or theorized at least. Okay? And the idea of the atom was actually brought up by this Greek philosopher named Democritus. Okay? It didn't catch on. It was right, but it didn't catch on. He said, I think that all matter is made of these tiny, indivisible particles. Not invisible. Yes, we can't see them, but they're actually not invisible, or you'd be able to see through everything, because everything is made of atoms. Okay? They're indivisible, which means you couldn't cut them. You couldn't make them smaller. They were the fundamental piece of that material. Okay? That was his idea. Now, unfortunately for Democritus, he was right, but people looked at him and went, dude, that makes no sense. Okay? We already got the 4 elements. Okay? We got the earth, air, fire, and water. And that makes a lot of sense, man. Like, if I'm looking at, let's say, because these are the Greeks, they've seen lava before. Okay? Volcanoes erupt in Greece. They know what lava looks like. Well, they would say that lava was some parts earth, some parts water, because it could flow like a river, and some parts fire, because obviously it's very hot. Okay? That was a system that made a lot of sense. You didn't have to be highly educated to understand that, yeah, these are the things that make up lava: fire, earth, and water. Okay? Steam would be some parts fire, and some parts water, and some parts air. Okay? Because basically you added those 3 things together, right? You put fire and water, and you got air. Okay? So it made sense. People could explain it. It was something they could understand, and they didn't require their imagination. Okay? Because you have to imagine tiny, indivisible particles that you can't see. Okay? So people are like, that's not going to work for us. Okay? Now, it wasn't all bad for Democritus. He was a Greek thinker on the same lines as Aristotle and Plato. Okay? That was like the sweetest gig you could have in ancient Greece. Okay? You sat in the Parthenon and people waved palm fronds on you, and you ate grapes and thought up stuff. It was a pretty good job. Okay? So it wasn't all bad for Democritus. He came up with something else that's pretty good. Any ideas? Sounds like his name? Democracy. Yeah, democracy. He went into the social studies area instead of the sciences after his whole debacle with the atom. Okay? But ironically, 2,000 years later, okay, he was proven correct. Okay? We do believe that all particles, or all matter, is made of these tiny particles. Okay, so I would say here, guys, if you're writing stuff down from this slide, I would say Greek philosopher Democritus came up with the idea of the atom 2,000 years ago. Probably good enough. Okay? You can always refer back to these notes when you're studying for a quiz or a test at home. Okay? But in terms of what you need to add to that or summarize, I would say that's probably a good summary of that slide. Everybody good? Can I go on to the next one? Okay. If you need it more, just let me know. Okay, so now let's talk about the alchemists. Okay, so the alchemists would have been like what you would envision of like the mad scientist kind of idea, a very like Da Vincian type of person. This is actually a picture of Leonardo da Vinci's lab. Okay, so they'd have had flasks and beakers and burners and all kinds of chemicals laying around. Okay, and they would basically do a lot of trial and error. Alchemy was trial and error. Today I'm going to mix these 2 things together and hope I don't blow up. Okay, I'm sure they discovered lots of explosive chemicals accidentally. Okay, as long as you survived to tell people about it, you were okay. Right, so a lot of just trial and error, but it was very secretive. Okay, the difference between alchemy and chemistry is the process. Okay, alchemy, trial and error, and secretive. Okay, chemistry, open, shared, and methodical. Okay, when we run an experiment in chemistry or any science that uses the scientific method, we have a problem that we're investigating. We have a hypothesis that is predicting what we think will happen or the relationship that we're testing. We have a list of materials we're going to use, a procedure we're going to follow. We have manipulated, controlled, and responding variables. And we run our experiment, we analyze our data, we come up with a conclusion, and we share it with our peers. Okay? And that way, if you come up with something in an experiment, it's like, oh my gosh, this is going to be groundbreaking, okay? You can have somebody else independently verify your findings. Okay? That's important in chemistry. The communication part is there. Okay? Does it sort of make sense? So alchemists, yeah, they did discover a lot of stuff, and years later it was kind of brought to light, but it wasn't something that was going to further society at the time. Okay. All right, anybody need that one anymore? Good there. All right, now the thing that brought alchemy to chemistry is the scientific method. Okay? Scientific method was developed by Roger Bacon and Antoine Lavoisier. That one's a good summary thing to write down if you're summarizing the slide. Okay? Chemistry came from alchemy via the scientific method developed by those two guys. Okay. Anybody need that one anymore?
What exactly does that mean?
So it basically means that Bacon and Lavoisier came up with this with the scientific method, which is a way to standardize how an experiment is run, basically. So now it doesn't matter whether it's chemistry, physics, biology, anything. We use the scientific method to test stuff. Okay, like maybe you've seen, like on YouTube, a good example would be if someone does a true comparison of two products, right? They use them in exactly the same way with exactly the same amount of materials, okay? And they control as many things as possible. Like, I'll give you an example. Like I watched the other day a comparison video between the new Ford Bronco and the new Toyota Land Cruiser. Okay, well, they're both the same kind of vehicle, but what's being tested is the vehicle. They're different. Everything else done the same. Same driver, same course, same amount of fuel initially, okay? Same kind of fuel initially. All those kinds of things that could affect how the vehicle would perform were kept the same. Okay? So we had a valid comparison, a scientific comparison of these two vehicles in this case. But you do the same thing with anything. Okay? It could be like two hair care products, or it could be two, kitchen devices, two coffee makers, whatever. Okay? As long as you treat the experiment the same for both of those things, it's then a fair comparison. Right? It's not like, well, today I mixed these two things together, and tomorrow I'm going to mix those two things together. But today I mixed 1 gram of this and 10 grams of that. Tomorrow I'm going to mix a ton of this with half a ton of that. Like, they're not valid comparisons, right? It's completely just, let's have fun. Okay? Yeah. That sort of makes sense?
Yeah.
That was their contribution, to find a method that would make it more valid. All right. So the idea of the atom. Okay? The idea of the atom comes from this. If I have a chunk of, let's say, lead, for example, okay? All of the atoms, for all intents and purposes, in that chunk of lead are identical. Okay? That's not 100% true, but we can say for all intents and purposes, every atom in that chunk of lead is identical. That's why the whole chunk looks the same. Right? It all looks like a dull, soft, gray material, a metallic material. Well, if I cut that block or that chunk in half, okay, do I still have lead on both sides? I do. If I keep cutting that thing into smaller and smaller pieces, all the pieces are still lead. Agreed? Mm-hmm. Their atoms are all the same. Doesn't matter how small I cut it. Well, if I could do this, if I could continue cutting until I had separated every individual atom in that chunk of lead, that would be impossible because I can't even see them, nor could I ever cut anything that small. Okay? Especially like with a knife. You never have to worry about splitting the atom when you're cutting carrots. Okay? The edge of your knife is thousands of atoms thick. Okay? You're not going to split them. You're going to crush them maybe, but you're never going to split them. Okay? So let's say I could actually keep cutting this block of lead down until I had an unimaginable number of lead atoms laid out on a table. Okay? Every one of those lead atoms would have exactly the same properties. Because every one of those lead atoms would have the same number of protons and the same number of electrons. Now, there's the possibility that the odd one of them might have a different number of neutrons. We call those isotopes. But Okay, the properties of an atom are determined almost entirely by the number of protons. All of those lead atoms, okay, would have 82 protons and 82 electrons. Okay, now the number of neutrons, that varies. Okay, to calculate the number of neutrons, we take this number and subtract that one. We'll get to that. Okay, but if we had isotopes of lead, which there are, okay, they could have more or less neutrons. Okay, but for all intents and purposes, we're talking like 90-some% of all the lead atoms would be the same. Okay. All right, is that okay? Does that idea work for everybody? Okay, so it doesn't matter how small I cut something, the smallest I can cut it is a single atom, and all those single atoms will be the same. Okay. Hello.
Good morning. We're just popping in to say good morning and welcoming our students back for another great year, or I guess for these guys their first year, but how are we doing? They look super.
They're bored to tears already.
They couldn't do with the atomic theory.
Yeah. Wait till we get to the Oppenheimer part of this. Then
They're used to waking up at 1 o'clock, you can tell.
yeah.
You can tell.
But at least you got some familiar faces, right? You guys know both of these guys, right? If you came from JP2 or St. Francis, right?
Well, welcome to HTA,
Yeah, welcome, Mr. Dornstadter.
Mr. Anacrito. Take care.
Good talk, guys.
Okay. So what I would write down from this slide is this part that's in bold here. Okay? An atom is the smallest particle of an element that retains the properties of that element. Okay? If we go any smaller than that, then we're just looking at protons, neutrons, and electrons. Every proton is the same. Every neutron is the same. Okay? If I took a proton out of an oxygen atom and a proton out of a lead atom, you wouldn't be able to tell them apart. Okay? What makes lead is how many protons it has. Okay? What makes oxygen is it has a different number of protons. Okay? We make everything out of the same material, okay? But we put it together different. Okay, so these are just a few of the models, okay, of the atom that we've had. Okay, the first one there in 1900, actually it was a little before 1900 that Dalton came up with the solid sphere model, which we'll talk about later. Okay, then this the Bohr model or the Rutherford model is the big one there on the left, and then our current one, okay, is the electron cloud or de Broglie quantum model. Okay, that is our currently accepted model. Okay, so we'll probably finish off with this. Okay, in the late 1700s, so after Bacon and Lavoisier had come up with the scientific method, people were running now valid, controlled experiments and communicating their ideas. People were starting to notice that matter behaved in certain ways. And they were looking for ways to explain those behaviors. Okay, they had noticed that what the alchemists thought they were doing wasn't really what they were doing. Okay, I mean, sure, they were running similar things, they were mixing similar things together, but the way the alchemists explained what happened wasn't what was actually happening at an atomic level. That's what chemistry was trying to explain. Okay, so for example, if I had an alchemist mix this stuff together, so if I had an alchemist mix this stuff together, potassium iodide with lead 2 nitrate, not lead 2 iodide. Okay. What would happen for both the chemist and the alchemist is they would take two solutions that are clear, they would mix them together, and they would get a bright yellow solid precipitate settling to the bottom of a clear solution on top. Okay? Now, the way an alchemist might explain that is, I mixed A and B and I got C. This yellow stuff. I mixed two things that were soluble in water, I dissolved them in water, and when I mixed them together, I got this yellow stuff. It's magic. Okay? But they would have thought that yellow stuff was something different than what they started with. They would have thought that what went on was this. A plus B equaled C. They thought that by mixing A and B, they were making something new, which wasn't entirely wrong.
So if they did believe that they make C, do they believe that they could like turn it back to A and B or not?
They probably would have thought that, and some reactions are actually reversible, but in this case, probably not. Yeah, some things, yes. Like the same reaction that allows you to discharge and recharge your phone's battery is a reversible reaction, but you have to put energy into it to make it go back the other way. Okay, so the alchemists would have thought, I mixed these two things, I made something entirely new, a completely different material. What chemists realized was that you actually had the same elements on the other side. You're not actually creating anything new, you're just rearranging what you had. So on the other side, you would have this. You would have potassium nitrate, which is soluble in water, so you wouldn't even see it. It would just be dissolved in the clear solution. And you would have this, lead 2 iodide, which is a bright yellow, insoluble material that was actually used in yellow paint back before 1950 when we used lead-based paints, and then kids would eat the paint peeling off the walls and it would cause developmental problems, so we banned lead paint because it's not good for you. Okay? So this is what a chemist sees, this is what an alchemist sees, right? The behavior of matter is explained differently, okay? When I mix two things together, I create different materials made out of the same base parts. I don't actually create something new. I don't create anything, okay? That was the death of alchemy. When we figured out that we're seeing these patterns, we're observing these things going on, we need to explain it, and the only way that explains it is if all matter is made of indivisible particles that can move around when they're reacted with each other. Okay, the 4-element idea doesn't work for that. Okay, we have to have another explanation, is that everything has its own atoms. Okay, so Dalton had 4 points to his atomic theory. Okay, the first one, he copied. He's a plagiarizer. He took that from Democritus. Okay, all atoms, or all elements, I should say, are composed of tiny, indivisible particles called atoms. Okay, should you write down Dalton and his 4 points? Definitely. Yeah. This thing comes up like quiz, exam, it's a big theme throughout the unit. Okay, I'll give you a minute to write those down. That's probably as far as we'll get today, and we'll talk about them tomorrow.